You are looking at a high-speed drone dive. Capturing this kind of extreme footage generates two things: thousands of low-resolution proxy clips for editing and a massive JSON file packed with raw telemetry data like speed, altitude, and GPS coordinates. Your client wants you to scrub through all of that data, find the exact moments where the drone exceeds 60 miles per hour, and swap only those specific proxy clips for the original 4K high-resolution files. If you try to do this manually, you will spend dozens of hours hunting for precise telemetry timestamps by hand. You will inevitably misalign frames, drop clips, or crash your timeline. The solution is to build a custom framework using ExtendScript. ExtendScript is Adobe's JavaScript-based coding language that allows you to automate tasks directly inside After Effects. This script will read the data, calculate the exact timeline offsets, and execute the proxy to high-res transitions for you. By shifting away from manual asset replacement and relying on logic-driven algorithmic instructions, you turn a 10-hour timeline management nightmare into a 10-second script execution. Step 1 is bringing the raw telemetry data into the After Effects environment safely. This means importing a massive JSON file, a standard text-based format used to store structured data, without crashing the software's older scripting engine. This diagram shows two memory capacity bars. If you use a standard string concatenation method, like typing result plus equals next line to parse the text, the left bar rapidly fills up to the top, turns red, and triggers a system warning. That standard concatenation forces the aging ExtendScript engine to constantly reallocate memory for every new line. As you see on the left, the bar shatters, causing a memory leak and a total system freeze. But on the right, using an array.push method neatly stacks small, identical data blocks sequentially without ever maxing out the total capacity. To safely ingest the file, you push the text lines into a JavaScript array one by one. Once the array is full, you execute an array.join command just before passing it to the optimized JSON parser. Mastering this memory management is the non-negotiable prerequisite. If the script exhausts the system's memory here, it will fail before any timeline manipulation can even begin. Step 2 is aligning your newly parsed external telemetry data to the After Effects composition timeline. This dual-axis timeline illustrates the core format mismatch you have to solve. The top axis displays massive integer values representing Unix UTC, a standard timekeeping system that counts the seconds since 1970. The bottom axis displays a simple relative counter from 0 to 10 seconds, which is how After Effects measures time from the start of a composition. To sync them, you calculate the absolute time offset. Watch as the vertical bracket locking the very first UTC timestamp on the top axis perfectly with the 0-second mark on the bottom axis, tethering the real-world start time to the video start time. You must avoid using standard seconds for your alignment calculations. As the two axes play forward here, notice how the top axis slowly drifts out of alignment with the bottom, creating a growing red gap. That cumulative drift error happens whenever you work with non-integer video frame rates, like 29.97 frames per second. To fix the math, you multiply your absolute offset directly by the comp.frameDuration property. Comp.frameDuration is an After Effects variable that defines the exact length of a single frame in seconds. When you apply it, the axes snap perfectly back into alignment, rigidly locked at every single vertical tick mark. Strictly enforcing this frame-based mathematics over simple seconds guarantees your telemetry synchronization holds true over long, complex edits. Step 3 is the asset preparation phase. Your script must locate the correct high-resolution media files hidden inside a massive project bin so it can prepare for the swap. This chart displays Big O notation, a mathematical way to describe how long an algorithm takes to run as data scales. Notice the red line curving sharply upward on the y-axis as the number of assets increases on the x-axis. This represents the catastrophic performance hit of using a standard linear search, looping through the app.project.items directory to find a file match for every single frame. The optimization technique is to build an AV item lookup table, also known as a hash map, exclusively during the script's initialization phase. An AV item is simply the ExtendScript object representing a media asset in your project. Look at the blue line appearing perfectly flat along the bottom of the graph. This represents O of 1 instant indexing, keeping search times incredibly low, regardless of how many assets you add. This lookup table pre-maps every file name directly to its corresponding AV item object in memory. When the script needs a file during playback, it queries the map and retrieves the asset instantly, bypassing the need for slow, repetitive loops. Moving from a brute force search to an indexed architecture is the dividing line between scripts that crash After Effects and scripts that scale limitlessly. Step 4 is the execution phase, where you instruct the script to trigger the actual footage replacement on the timeline. The core logic requires a trigger. When the parsed telemetry metric, like the drone's speed, exceeds your predefined threshold, the script targets that specific proxy layer for replacement. You execute the swap using the replace source command. You must pass two arguments, the high-resolution file from your lookup table and a Boolean value set to true. That true parameter is absolutely required to preserve any existing expressions or keyframes already applied to the layer. The final technical addition is injecting marker value objects onto the layer at the exact frame the transition occurs. A marker value is a data object that allows you to attach text and variables directly to a specific timestamp on the timeline. These markers act as metadata carriers. They write the specific speed and GPS coordinates from your JSON array directly into the timeline, making them visible to the user and accessible to the render engine. By embedding this data, you transform a sterile sequence of isolated video clips into a responsive, data-rich timeline environment. With the logic built and the assets indexed, you execute the framework with a single click. On the timeline, the dull proxy layers instantly convert to sharp, high-definition thumbnails, perfectly timed to the speed thresholds. Simultaneously, a cascade of brightly colored metadata markers populates the layer tracks, organizing the entire edit. Mastering dynamic asset swapping saves editing time, but more importantly, it forms a direct, automated bridge between physical real-world telemetry and high-end digital visual effects pipelines.